Hey everybody, we're going to get started, so please find your seats. Welcome to NLSea. We don't need that anymore. There we go. In case you haven't been to NLSea before, the goal is to share knowledge about practical and modern applications of NLP. What does that mean? I don't know. We come together, talk about cool projects, talk about recent papers. Just help more people get into NLP and talk about the wins we've had, the challenges we've come across, that kind of stuff. We do have a code of conduct. It's puppies. It's really simple. Just be nice to each other. It's not something that's telling you how to act. It's just invest in each other. We're all part of a community, you know. We do also have a Slack channel. It's NLSea on the puppy Slack. So get in there for great links about how Microsoft is making models that are way too large. Thank you to One Piece Work for hosting. They've been really helpful throughout all of this and hosting us. Unfortunately, the Seattle office is closing today. So yeah, if anybody wants to host, let me know. But I'll probably be looking next time I actually schedule something. So. And if you have a talk you want to give, we do actually have another speaker, which is wonderful. Thank you so much. It's really not that bad. So if you just have a cool project that you worked on, or something that you tried out, let me know. We can accommodate talk formats from short to long, all that kind of stuff. It doesn't have to be the fancy state-of-the-art stuff. Please. And that's it. So I'll be giving the first talk. I'm opening for an amazing talk about transformers later. So I'll be covering language modeling sort of in general. Bird's eye view kind of. Unfortunately, there's not going to be any code this time. I'm sorry. But it just wasn't achievable given the things we're covering. So language modeling. And its amazing implications for, which, thank you. There we go. I was hoping someone would get that. That's a language modeling joke. I'm Stuart Axelbrooke. I make a cool thing called Tag It. You tag things, and then it learns to tag them for you. So if you have some text categorization needs, you don't want to keep paying humans to do this stuff, it does that. Come talk to me. I also do some consulting via Thought Vector, so if there's anything maybe a bit more bespoke, come talk to me. But I came here to talk about language modeling. And what is language modeling? Because that sounds pretty vague, right? The classical definition of it is predicting a word from its context being the N words that preceded it. I feel like that's a little bit too restrictive because now we've got much more interesting targets that we talk about. But I think you could say from like a broader perspective, it is language understanding via unlabeled text. So testing some language understanding task and training it on unlabeled text, like next word prediction. Here's the funny picture. This kind of, the subtitle should be, a bad language model, I guess. But yeah, so honestly, language modeling does kind of sound boring. If you talk about like, oh yeah, just fill in the word, nobody's going to pay you for a fill in the word API, right? But language modeling has become one of the more important NLP tasks in that it enables us to imbue models, and it sounds kind of anthropomorphizing, but imbue models with understanding of text that we want to do other tasks on. So, imagine someone liking this. Any human can see that, or any fluent speaker of English can see that and say, okay, that person's being sarcastic. They think that thing is not very good. And that's something that actually from the literal words in there would be hard to pick out without that context. So language modeling helps us, pour tons of data in there and then move on to downstream tasks and be able to pick out those nuances and apply them to our specific, business-specific task without having to label a giant data set, because paying humans to do that is very expensive. Also, for some concrete stuff, language modeling as pre-training has been shown to give us new boosts in state-of-the-art for a lot of tasks like question answering, co-reference resolution, that kind of stuff. So the format of the talk is going to be starting with the n-gram models, which are pretty much where language modeling as a thing started back in '92. Moving on to more complicated stuff, people talking about distributed word representations, recurrent neural networks, and everybody's favorite thing these days, transformers. So, way back in the day, '92, I mean, I was alive then, yeah. IBM prepared this paper, did all this work in doing language modeling, which they formalized as you have n words, or you have n minus one, n words, and you predict the nth one, right? Actually, I got that wrong. Sorry, that was their approximation of it. The actual model was you have a document which has words in it, and you use that context up to a certain point in the document to predict what the next word will be. And since their computers were not that great back then, they had to limit it to a window of like 3, right? So this was a very simple attack on the problem, which is sort of good and bad in that it was very understandable. The way that they predicted the next word was essentially saying, okay, we're just going to go through the entire corpus and just count for the previous 3 words what was the next word. And then when we want to predict on some new example, we just go look up the last 3 words we saw, and then that over the total corpus size is the likelihood that is what not corpus size, but of all of the next possible words, that's the likelihood that the word will be that. That sounds great, except you can't observe all of English use or any language use, because you have a bunch of people here talking, a bunch of people sending private emails to each other, and also it's just computationally not feasible, especially when your n-gram windows are getting larger. So that touches on the sort of shortcomings they found in this model, which were recursive dimensionality, where you need this really large vocab to represent all the things that humans talk about, which when you have computers from 1992 is super not possible. Even today is still not possible. The n-gram space is super sparse, so you don't say there's some uncommon set of words. It's likely that it just won't exist in your corpus, even if someone will speak it in new data that you want to use in your model. And there's no notion of word similarity. So after that, you kind of think that knowing about the and an would give you some information about each other, about when to use each in a given word that you're predicting. But those are just, by definition, different in the way that they built this model. So they couldn't utilize that word similarity that we sort of implicitly understand. Also, long-range dependencies just didn't happen because you have a word, there's a trigram model. Anything more than 3 words ago, it just doesn't exist anymore. So those are like incredibly significant problems, but in spite of that, they were able to actually create a workable language model, I'll say. By today's standards, very not good, but it was the first thing, so what are you going to do? Oh, yes, and they established perplexity as a metric for evaluating the quality of language models, which kind of has fallen out of favor because it's hard to compare across data sets, and we've realized that downstream tasks are very important for establishing the quality of language models. But in case you wanted to know what it was, because people talk about it, and for the first year or so when I saw that, I just never really understood what it was. It's the geometric mean of the inverted word likelihood for each word of the document, for each document in the corpus, which is essentially saying that every data set has an implicit perplexity, and your model, if your model reaches that perplexity, then it has learned to predict the corpus perfectly. So it's more of a directional metric than, say, something like accuracy, where you know once you get to 100% accuracy, you're done, right? So I'll be talking about reductions in perplexity here for some of them, instead of talking about other metrics, because this is what people used for a while before we moved to downstream task evaluation like glue, squad, that kind of stuff. So this is when things get interesting, right? So if you recall the n-gram model, you can imagine like a giant hash map of, okay, we saw I went to, and then there's a and the, right? Like, say we have 4 words, and we record the amount of times that we've seen that happen. And if we want to use I went to the, we find everything that precedes, that is preceded by those 3 words, and then find the most likely answer within that, right? You can imagine how many combinations, I should have made a clipping of it, but there's a ridiculous number of combinations of all possible 3-word n-grams. And Bengio, very clever, thought, oh, we obviously need a distributed, well, actually he didn't. Hinton originally said we need a distributed representation for words, but Bengio did the work to make a language model that did it. And this is pretty much where we got word vectors. He said, okay, if we can use a neural network to learn this distributed space of words, then suddenly we'll have meaningful distance between these words, and the model will be able to use that to make decisions about what the correct next word will be, thanks to that word similarity that we'll get from that embedded space. Didn't use any of those words. If you control V there, you don't get any of them. Vector and word, but it worked very well. The only problem was that neural networks are super expensive, and back then they didn't have any of the software optimizations that we do today, and also the hardware was just not as fast. So he did some hacky stuff to make it happen by limiting, okay, we're only going to look up the most common 1,000 words. And it still achieved great results, but there were obvious limitations in the computational capabilities of it, where if you wanted to use the full vocab in your neural network, it would just take prohibitively long. And that was actually, I'm not sure I mentioned that for the n-gram model, they had to limit the vocab size to like 5,000 words, I think, which is like insane. That is like, even recent subword vocabs that are meant to be very small are an order of magnitude larger than that. So, what's up?
Did stemming exist back then?
Yes.
So they did still do stemming?
Yeah.
Okay.
And they did some clever stuff, and the data sets they were using, they didn't have Twitter back then. But the data sets they were looking at were fairly clean. But even still, they did actually do something called word classes to coalesce similar words. So they approached some of these problems, but they did it through statistical means, not by discovering some embedded space. So you can kind of see how each of these improvements is a progression on ideas that or problems that they were aware of and they tried to solve, but just didn't have the either computational ability or the belief that neural networks were worth anything. Yeah, so the learnings from this paper were that longer context is obviously better, and that more parameters seem to make it better, like make improve performance, reduce perplexity, but that it just wasn't feasible given the computational capabilities. So this is sort of an enduring theme that we just, what's the Star Trek thing? She needs more power, Captain. Which leads us another 10 years. So it's essentially like every 10 years something big happens in NLP. To RNNs. And this is like vanilla RNNs. This isn't LSTMs. This is I think the first one that I could find that applied RNNs to language modeling. And while Bengio's got a 35% reduction in perplexity, which is really large, RNNs with less than 1% of the data size for training achieved a 50% reduction in perplexity. So these things just, neural networks came in and they continue to change the world for NLP. But the big reasons that they could is that before we had bounded context. These long-range dependencies that we think of, imagine this is pretty much one continuous run-on sentence. Analyzing this with n-grams would be not very useful. But RNNs, in theory, would allow you to capture everything in the sequence that you're analyzing and not having to worry about a window that you have to accommodate or, allocate more memory for, that kind of thing. Yeah, but even still, the reason that they trained on that little data is because they just they didn't have an efficient implementation. And at this point, they were using, I think it was BLAS, to give them more horsepower, but still just having RNNs are expensive. So that brings us to the heavy hitter, transformers. And this, up until this point, everything has been, okay, we know these computational problems, and we know that these RNNs can learn arbitrary functions, and language really kind of feels like an arbitrary function. And by applying more neural networks in more intelligent ways, they really keep performing better, but we just don't have the computational power to do it. And BERT is really the culmination of that, or maybe the most recent significant step, in that they figured out how to go for, so RNNs are hard to compute efficiently because of the time aspect, because you are looking at one after another time step, and that you can't do optimization on the next time step until you've calculated the previous one, even if you do loop unrolling. And one of the things that BERT changed is that it took self-attention and made it so that you could achieve time dependence in these things by adding a positional encoding, so that the transformer could look at, okay, what's my token, what position is it, but also what is going on in the rest of the sequence, so that I maintain that context that the RNN is getting, but without relying on having the previous answers or having a previous. So it meant that you could implement this language model completely parallel, and it meant that distributed training, even when you talk about distributed over a single GPU, was much, much faster. Yeah. And also, one of the other great things that it did is that they went from next word prediction, which had been the target for the whole time, to something more intelligent, because humans are sitting there listening to stuff, and I mean, there's times when you realize the importance of something that was said 5 minutes ago, right? So it gives the network the whole sequence and masks certain tokens randomly, so that it can say, okay, now predict this one, now predict that one. Along with that, they added a sentence order prediction, which they would give it 2 sentences and say, okay, is this in the correct ordering? And that meant that the transformer model had to learn a different understanding of the text, something that's not just word replacement. Because if you think about understanding a single sentence, then something that followed it, you have to understand something more deeply about the intent, the direction of it, to say which one should follow the other. Whereas word replacement, or word placement as a task, it can be done pretty well statistically. Yeah, and that really, you can summarize that stuff pretty quickly. Pretty much, we want to make it easier for computers to compute these tasks. Allowing larger vocabs, better tokenization. You guys saw us over tokenization. Enabling long-range dependencies, because a lot of times you start a sentence with something important and it's referenced later. Neural networks are really great at approximating F, and that means that we don't have to build statistical models of language and rely on those, because those can be very brittle. We have GPUs now. GPUs and TPUs. Honestly, so much of the progress has just been utilizing like these incredible co-processors that are GPUs, and like being able to efficiently put the data there, get it to do the backprop, and getting it back and having that information flow quickly. That it's kind of, there's a paper about this actually, about how all of the progress is essentially just using more hardware. And I mean, if you'll take a few more complaints, the whole 17 billion parameter thing that Microsoft did, it's like, great, you trained this on 1,000 TPUs for
6 months.
6 months? Okay. I mean, that's like, it's incredible, and it points to the direction that we're going for producing language models that really approach human capabilities, but at the same time, it's a bit frustrating. Anyway, also, this is the one that excites me, which is like new training targets that we can use for unlabeled text that require different aspects of understanding of that text. And I think that that's about where things are headed. Larger, more efficient, and I think that efficiency is a big part, because TPUs and also work that graphics companies have been doing to enable ML on their cards has done a lot to make this stuff accessible. But also more training targets. Something like sentence order was very creative, and yeah, that's where things are going. Questions? Comments? Thank you.
So, since this is language modeling, could you just talk about how it goes across various languages? Do we need totally new data sets to even make any progress, or can they adapt to these like unseen languages if we trained it on the English Wikipedia, and then what happens when we go over to Korean?
Yeah. So the exciting thing is that they still work, at least for human languages. Once we get one of those alien ones, we can test it out. But I don't know of any modifications made for languages that aren't English or German or anything like that. They still, in fact, in the tokenization layer, the multilingual BERT still just goes to, okay, these are tokens. They're in different languages, right? Like there's 7 is in English, and like Word IDX 2003 is in Afrikaans or something, but it gets mapped to a space that is not explicitly languaged, I guess.
Cool.
I was curious, has anyone done comparative studies of one language versus the other in terms of performance?
Yes.
Okay.
And it maps directly with available data. So English
Okay.
English is kind of easy, and it's, or compared to other languages, is very easy. If you look at low resource languages, where say they don't have a robust Wikipedia, or there's not some giant public data set, say a platform that's well used by people like Twitter, then it gets much harder. And that's actually where language models are very exciting, because you can learn, the language model can learn about sort of this is anthropomorphizing it, but like about the shape of the human experience. And then with more data from a language can learn to map from that language to this shared model of the world. So the joint training on a bunch of different languages is a very exciting thing that people are looking at right now. There are some models like the BERT multilingual one that do that, but I haven't done any direct comparison of effectiveness on models.
Okay, so you're saying like if you have a model that's trained on English and then you take it, do Korean, it actually reaches performance faster than doing it from...
Yeah.
Okay.
So what about multilingual data? Like mixed, you have a sentence that's like half English, half another language, whatever.
Oh, so like within the sentence it's split.
Yeah.
English.
Oh. I'm not sure. I mean, I think it should work, but that depends on like how often people do that. Because what's the word? Like if a sentence is solely one language, that happens frequently. But But yeah, I don't know. I honestly, so I haven't worked with language models directly much. This is just a bunch of research I did, so grain of salt.
You know how with all these models, like for punctuation, do they treat them as words or is it separate?
That depends on your tokenization scheme. A lot of people will separate the punctuation out, like in, for instance, can't, what do they call those? Words. But yeah, they'll split those apart. Sometimes people will remove them, but I generally think that you're better off leaving the input data less filtered. Because if you have enough, and this is the thing, is there's tons of text data out there. If you have enough text data, then your language model can learn to use that stuff. So, all right, thanks. Next up, we've got Gabriel with transformers and fun things you can do with them.
Yes.
All right.
So, other than sharing titles, I think Stuart and I did not coordinate, but hopefully they'll be complementary.
Make sure the OBS thing works.
Yeah. So, OBS, click.
Start recording.
What you click.
Okay.
Great. So I will make the opposite apology that Stuart made, which I didn't intend to send you to show you any code, but you're going to be seeing some code. So the purpose of this talk here is basically to introduce the transformers that Stuart mentioned by way of a word game. But the actual purpose of this talk, like the takeaway that I want you to feel, is that it's a good time to be a beginner in NLP. So there's a lot of developments in the field. There's a lot of cool tech that would not have been there some years before, and maybe you've never done machine learning before. Maybe you've never written any Python before. It's still a really great time. So sort of I guess I'll give a third reason about this talk. I was really excited to discover this venue last time I was here, and kind of wanted to prove to myself that if it is a good time for a beginner to be in this, then I should be able to put something together and give a talk. So you're sort of seeing the result of that. We'll see if it works out or not. So just a brief second about my employer, of whose views I'm not expressing. All views expressed here. So I'm at Seattle Cancer Care Alliance, or a cancer hospital, coupled with cancer research institutions. We're starting to wade into a space where we've got a bunch of problems with NLP components. So we're learning it on the fly. We have a team with background in data science and machine learning, but new to NLP. So my contact information, if you want to note it down. So here is sort of the current and original outline of the talk. Sort of, trying to bite it a bit more than I can chew, but we're going to do a word game, and that word game is going to lead to this transformer architecture that was mentioned before. And that will lead in turn to discussion of future work. And I'm going to have to keep track of the time because our CloudWatch event is going to boot me off of this server in a bit time. So I'm going to introduce the rules of the game. You're provided a word. The definition is hidden. And 1 out of every 3 provided word definition pairs are bullshit. Totally made up. So based on this provided word, every player tries to come up with a definition that they submit in secret. And then in the last step, everyone tries to guess out of the words and definitions they see, the correct definition, but also they might just call bullshit on the whole thing, that we think none of this is all made up. So to give you some examples, so here is a word with a bunch of definitions. Can I get 1 or 2 volunteers to play the game? 1? Let's get 2. 2. Okay, great. So point out the real word.
Largent.
So largent is a real word. Could be real, could be fake.
Bullshit.
You think it's bullshit? How about you?
I think it's a real word.
Yeah. which is the right definition. Only one of them can be right.
I'll have to do both tasks.
Make it larger.
Okay, can you make it larger?
She's out on her grace.
Okay. Turns out, bullshit word. All these are so let's just, in the interest of time, we'll do one more. So
Tacoon. Pretty sure that's a piece of wood or sheet metal fitted into a ditch.
I'm with him.
you guys are right. We'll skip this one, but you sort of get the idea. So this data, the real definitions at least, came from a dictionary, and so I'm going to get into some of the challenges in developing that data set. So dirty data. Not all words that are in dictionaries are good words for this game. And it's difficult to identify rare words, which I'll get into what I mean about that in a second. So the high-level process for preparing this data is sort of here in this. This is actually not, this is pseudocode that I just wrote in Python, formatted as if it were Python that actually ran. But, I've got different source dictionaries. We'll do some normalization, filter out some words, which are the good words, and filter out some definitions, which are the good definitions, and then do some training on those. This is, sort of boring stuff, but you have to do it. You're going to find, bits of dirty data, weird words that aren't weird at all, encoding problems, empty entries. This is sort of like real data. And so it never ends, right? You always discover these kinds of problems. But even the words that are good words in the sense of not being dirty are not necessarily what you want. So you'll have dictionaries will have these compound words where, we all know what C and card is, and we all know what term and policy is, and if you just make these compound words, they're cluttering your dictionary, and where you can infer the definition just by looking at the two definitions separately. So we want to remove those. Similarly, there's lots of these sort of reference definitions that'll say see the definition of this thing, and those are also sort of not really great for these games, in that we want people to sort of look at the actual definition and guess the word. So gotta get rid of that. And this is you also have sort of half words that will end up in dictionaries. So some prefixes, some affixes, which are generally these are common things, but still we don't want them in the game. Multiple definitions that will end up in this case delimited by semicolons. You can have sort of written delimited ones as well. So try to find these, and the heuristic I'm using is just take the biggest one. And so when you do all that, you start to get a data set that looks, starts to look a little bit cleaner. Still not totally clean. You can see there's some problems here, there should be a space in between them. So it's been an obnoxious problem with some of the dictionaries that I've found that they're not sort of correct like that. But yeah, that's, we've got some words that I didn't know what that is or that is, and maybe I could have guessed what that is, but here's a common word. And so that brings me to sort of the next, sort of actually what I ended up spending a lot of time on, which is we want this game to be based off of rare words, because we sort of want to guess is this word or not? Is this a real word or not? You sort of want to have to be able to guess that. And so, you can read online that adult English speakers know something like 40,000 words for native speakers, something like 30,000 for educated non-native speakers. But the word frequency does depend on context. So if you work in one field versus another, you might know your own sort of specialized vocabulary. But basically, for this kind of first pass, I just found a Python program that used some canonical sort of book corpora, and just exclude the most 40 common words according to this Python program as a first pass. But that doesn't quite do everything, and this is the I'll happily apologize for showing this code. That doesn't get you everything because so English is mainly analytical, an analytical language, meaning that like words are sort of atomic, but there are like modules in English that you can kind of tack on like prefixes and affixes to make like if I just define this word NLSea that's like not in any dictionary, as soon as you know that, you can like know what pro-NLSeificationism is if you know English. It's going to be a super rare word, right? So we want to, you can get lots of rare words in terms of their frequency in any corpus by these sort of rules. And so we want a way to like account for that and factor that out because we don't want people like, getting inferred definitions. And so like the current like strategy that I'm using is to just have some heuristics to identify that base morphology, that is sort of the core of the word, using like stemmers and borders, or stemmers and rooters. One from NLTK, one that I wrote by hand. And then so what I do then is like every word has a basal form by this heuristic, and each of those words have frequencies in the corpus, and the effective frequency I assign to all those words is the maximum of the ones amongst their shared base. The current heuristic, which sort of gets at the idea that if a base form is sufficiently common, then like maybe people know this and recognize the word. So sort of like this kind of like stemming and like rooting isn't necessarily enough. Have you ever seen mice use mouse to corral a pack of rabid mongoose through a series of hyperbole? So this is sort of getting at the idea that like it isn't just like sticking words onto other words. There's like inflectional morphology, so like changes in the sounds of things that can happen as well. So like mice, there aren't mices. There aren't mouses. There's mice, for example. There aren't hyperbolas. There's hyperbole. So in particular, lots of scientific vocabulary will have sort of Latin and Greek inflected forms that can really sort of explode in terms of the number of possibilities, but if you kind of know the field, you can kind of infer their meaning. So I made some effort like trying to like deal with this and just like gave up. Partially because like the toolkits that I found just weren't like, especially on this sort of like scientific subset of words, they just weren't really good. This is called lemmatization, the process of getting this sort of base form through inflected morphology, and yeah, I just like couldn't really like get it to work in the way that I wanted it to. So I sort of gave up, and like post hoc justified that to myself because does anyone see the problem with this sentence? How many, if I have one mongoose and I have another, how many mongoose do I have? So mongoose is not a word. So mongooses is the correct plural form. Like, you would have to be a native English speaker to know that. It's like not even native English speakers get this sort of stuff right. So for the purposes of the game, if it's kind of confusing, that's actually good. So we leave it in. Okay, so now we've got a bunch of real definitions that are like rare definitions. But we need like made up words and definitions. So how do we do that? So Stuart gave an introduction to transformers before. I'm just going to check my time here. And I'm going to try to sort of rehash that. At a high level, like one way you can think of transformers is that you take a sentence, and that sentence gets broken up into a bunch of tokens. And from the tokens, you've got this cascade within this neural network, where every token has a vector, just a bunch of numbers behind it. And those get put through some process, which is just, that's a word salad right now. It doesn't have to mean anything to you, but there's a sort of a recurrent process that takes a bunch of input vectors and gives you output vectors, one for each word. And then from those set of output vectors, you can solve problems with that, which there are different problems that you can solve. The kind of output you get is task dependent. So kind of try to keep that all loaded in your mind. We'll start like diving into some of these details. So so this is like, I'm pulling a I'm pulling, I guess, an actual real definition. I have to scratch my head for a second because I forgot what's real and fake and like in the process of making it. But this is a real definition, a real word and a real definition that we pull out. And I think you can think of them as a special kind of sentence definitions. A sentence that starts with the word and then like follows up with like, actual sentences about the definition. And so a couple of things that you'll see here. There's this additional class token that we're putting in here, as well as some separation, I guess we're using a second separation token at the end. The word Rakidian here got broken up into like different token subwords, which the double hashes mean that it's essentially a suffix. If you don't have a double hash, you're a prefix. And so these are all of these sort of things they're just a series of numbers. Those numbers index the vectors, these like word vectors that Stuart introduced before. And that's sort of like what tokenization looks like. And so say in a second what these are all about. Oh, so then you can this is just taking a look at, in this tokenization scheme that I have, after getting out all my rare words, this is sort of like a look at the top sort of frequency in that dictionary, which the dictionary I have, by the way, it works out to like, something like 50,000 words, I think, is what I had, after like doing all the filtering. And these are what like those sort of prefixes look like and what those suffixes look like. Let's get an example of what these things are. If you were to go down to the bottom here, you'll get more, the words will get longer. You'll see like really specific things that you imagine, like maybe it only appears in like one word as a prefix, and then it has a couple of different suffixes. So, there was this sort of thing of like self-attention plus feed forward neural networks. What's that all about? So I definitely punted here, so we'll see. We might have to do a Q&A to get down to some of the details here, but copied this from another presentation I was giving. So this is sort of like repeating that you've got your words, and you have behind your words tokens. And each of those tokens has a vector behind it, just a series of numbers. And it has that devoid of context. So like if you just pull the word have out of nowhere, it's got a number associated with it. But the word have doesn't really mean much by itself. You have to kind of attach it to a sentence for it to be imbued with some meaning. And that is what these transformers kind of allow you to do. So this is just going to be a black box here, but at a high level, this self-attention module lets the vectors to interact with one another, to see how much they line up with one another in one way or another. And based on how much they line up, they can sort of perturb one another's direction where they're pointed. And after you do that a couple of times, you get, there's more going on here in that there's like this feed-forward network, which does nonlinear transformations. There's a skip connection, there's like a recurrent connection, there's layer norms and all other kinds of stuff. But basically the picture is like, eventually you end up with vectors for the words that are context dependent, that are like sensitive to the actual sentence that you have. And that is, that is cool because different transformer architectures have different kinds of pre-training tests. So what do I mean by that? So pre-training is the training task that you train these things on before you solve the actual problem that you want to solve. And BERT is the particular transformer architecture that I'm looking at, and it optimizes for a closed task, and in next sense it's a supervision task. Where what a closed task is, I'll just show you. The idea behind this closed task is, so we start with this situation, and now you imagine like swapping in the different, masking out at random some of these words. And you run it through this module, and the idea is that that word, which is initially devoid of context, for each of the words, will gain context from all the other words it's surrounded by, and eventually come out with some context-dependent representation. And that can be fed through a softmax, basically, and you'll get a probability for each of these masks that's sensitive to all the other data, is the idea. And so, in this sentence, words have meaning maybe, they maybe have power. They can have like Chinese characters as well, because that's in the corpus, but low frequency. Similar to the other one. So that's sort of one of the tasks that you're optimizing for. the other task, like I forgot to mention, but this separation token, what it's doing is separating like kind of two sentences. So that's where this special class token comes into play. Because the use of the class token is the following: that during pre-training, this BERT algorithm can either like give sentences as they are in order, words have meaning, the meaning depends on the context, or they can inject, and they do half the time, a sentence that's from another context. Words have meaning. I'm gonna go get pizza tonight because I'm super hungry. Like, maybe that second sentence seems less likely to follow that first thing. And that's something that you can estimate through this class token, which again gets dumped through a softmax. And so that sort of, and I'm not trying to get here into the technical details, but rather to stimulate your imagination. That sort of sounds familiar, right? Like this is not unlike if my sentence is like just one word, which is this rare word, followed by a definition in a dictionary. This is sort of like a game a little bit. So here's like a proposal for an algorithm that can exploit this task that BERT has been pre-trained on. So I can take a word from the dictionary, and like half the time I can basically say, I'm gonna mutate this word until it doesn't look like a word in the dictionary anymore. Sorry, a third of the time. And I can do that by like replacing, up to some number of times. And then once I have that word, which is either a real word or like this fake word, I can get a bunch of definition templates. These particular numbers don't matter, they're just like what I'm doing right now. And from the templates, the templates basically are sentences with masks. And I can fill in the mask using BERT's mask prediction, which has been trained to do. And then out of this sort of like 8 times 16, sort of candidate made-up definitions, I can choose the top 3 or 4 fake definitions, where the reason that I know how to choose the top 3 or 4 is that, again, that class token gives me sort of effectively translates into a score that says, does this definition, is it likely to follow this word? So here's like an example of word generating a fake word from a real word. Can you guys see which one is the real word in this list? Shout it out, just be bold.
Bring it.
Yeah, how did you know? Or just a guess. You could infer because this is a short word with only 2 tokens, there's only so many ways you can like swap things out. In this case, they were both replaced, but you can see that there's an ent and a ring in these other ones. So one token was replaced here, one token was replaced here. And so yeah, you can sort of like, it's likely that ring ent was the original one. So you're right. And the rest of these are made up words that don't appear in any dictionary. Which you do by filling in masks. This is like a problem that BERT solves. So similarly, so it's a bit more complicated to get definitions, but the strategy that I used, again, was to come up with these templates, which all the templates are, well, I'll say in a second what they are, but like, suppose these were your templates. Then you can, using that same technology, fill in independently each of the masks, is what BERT does. I actually do something slightly different, where I fill in the first one, I fill in the first mask, and then set it, and then sort of left to right, re-infer what I should be filling in. This is sort of like to get around some limitations of BERT in particular. There are other transformer architectures where I could do this more flexibly, but sorry, that's probably into the weeds. I don't know. This is the game, right? Like, could anyone want to say, like, is this a real word? What's the real definition? Yeah.
May I ask a question?
Yes. Yeah.
Because I saw it in the last slide. One of them made up what happens if you have a case. I'm looking at the one index dual, DOOL.
Yeah.
What happens if you have a made up word that is a close approximation of a misspelling of a correct word? Because dual,
Yeah.
DUEL, is a real word.
Yeah. Currently, nothing happens. So yeah, yeah, in general, I generated these
Mhm.
and sort of selected, you can see I'm controlling the random state here, sort of selected which was good for the presentation. These are actually quasi-representative, like it actually works pretty much like that, but yeah, that would be, I haven't done anything to account for misspellings.
I have a similar question, which
Yeah.
is curiosity question, about a scenario where, say a word like bazinga, which is not a real word, but becomes a real word, and how this, just out of curiosity, how's the output for this kind of model?
Yeah, like words that, is your question like, if a word sounds like a real word, or?
Yeah, or I'm thinking more in the direction of the language evolution. Sometimes, there's some kind of like gap, how it's becoming catching up, something becomes like a non-word stuff becoming a word.
Yeah, so Bazinga in particular, I think I get what you're saying now. Maybe this isn't your question, but I'll fill it in a question that's interesting to answer. So like, there's just weird words that like are surf slang words that become popular for whatever reason, and like, they maybe are invented like last year, right? And like, they're not in any dictionary, and so like, how do I deal with those? Again, in the particular bit of software I've like crawled, smashed together in the last few weekends. Nothing. I don't do anything to model that here, but that's not unlike like the goal of what we're trying to do here is like, so bazinga is like an English word that somebody made up at some point. Probably blah 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 could also be an English made up word, but that doesn't respect like good English phonology. So if you saw that as if someone was trying to tell you that blah 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 was an English word, would you believe them? So like, part of what you want to get right here is like respecting the right relative frequencies of phonemes. We're now in weird territory. Let's see if this keeps serving me. I knew there's a CloudWatch event that was going to kick me off this server in a second. But yeah, so I'll maybe have to try to answer your question better later on. Good, yes. Okay, so going back, I think we were here. I'm just going to, next time move forward, that there it was, like the real definition, and these were the ones that were filled in. So yeah, just a brief comment on how I made these templates. It's a total ad hoc kind of process. I think I was talking with someone in the crowd earlier who was talking about language generation, and like this is not like a canonical or a state-of-the-art language generation. This is kind of an ad hoc process where basically what I do is like take the actual definitions in my dictionary and just using parts of speech tagger, like identify these parts of speech, and some fraction of those I like mask out. And yeah, that's how I get these templates. It's sort of crude, but like seemingly worked for what I wanted to do. I'm currently doing this with Spacey just because like it was there and I grabbed it and it worked. But this is something that you can also do with the transformer architecture itself by basically changing that head, by changing that last, if instead of solving that masking problem, you just allow the weights in that last neural network, in that last feed-forward network, to change a bit in a transfer learning type of situation. And you can also solve like parts of speech tagging using the same sort of basic module. Basically get all of the words up to its last context and then just slap on a different task. So sorry, that was, I don't know how much sense that made, but something that I wanted to do. So yeah, just kind of one more quick thing on the template generation. They aren't always good. Let me make the font smaller here just so you can sort of see a bit more of what is going on. So this is a template that I got out of my dictionary, which like wasn't that great. And sorry, it's kind of hard to see here, but basically there's a bunch of masks, but only one of them changes in the way I sampled it. Yeah, it's like you have an organic compound, an organic liquid, and an organic liquid, and none of the other things changed. So I probably need to do some work to like, maybe this is just a bad kind of template thing in general because it's like particular to some like kind of chemistry question, and so it isn't going to necessarily match with the word. But then also like, yeah, something about like, diversifying these samples might be also in order. And so what I wanted to originally give the talk on was the topic of fine tuning, which I sort of alluded to just before. So the current like random thing that I like brought together works surprisingly well. So I was showing you actual sort of how all this hackery like turned out like kind of reasonable looking definitions. But what you could, if you wanted them to look even more reasonable, you can do what's called fine tuning. And this is basically, so BERT was trained on a corpus, which is like a bunch of books and like Wikipedia articles or Wikipedia comments. And those are just like, they look different from dictionaries. And the idea of fine tuning is like, you can take basically your architecture trained on one corpus. And if you've got another corpus, which is still like English, but just is a different type of English, like you have in dictionaries, then you can sort of tweak your parameters. Maybe not tweak all the parameters, maybe just tweak the last layer of your network to sort of more realistically model that particular corpus. And so, yeah, that's something that's cool. Probably gonna do it. But this is also a good point to like think for a second about like what am I actually trying to do here in making this game? Like part of the game is about sort of faking out definitions. But so I used to play like a related game called Balderdash with my family all the time, and we would have fun. And like some of the fun was just like definitions that everyone knew this was the fake definition, but it was like so funny that we had to vote for it, right? And so like, which again, sort of commenting on, let me go back, the flexibility of these transformer models is that if you decide to change your task, if you decide like, I don't really care about faking definitions, but I care about like funniness, what you can do is take that last class context vector and say like, yeah, don't optimize just for faking people out, but optimize for like how funny it is. That you can have a classification. If you have a data set of like, these are funny definitions and these are not, then you can classify and see like, relatively speaking, how funny you are in a context-dependent manner. So that's sort of like, kind of to give you a feeling of one of the reasons that these transformer architectures are cool is they're really good at this sort of adaptation to specific tasks. Yeah, again, sort of like my initial ambition was like, I'm gonna like make an app and like deploy it. I still want to do that because I think it would be cool, to have a version where like humans are pitted against bots. So like these fake definitions are being made not just by the algorithm but by people. And like similarly, people can sort of annotate like, was this funny or not, or did I think this was the real word or not? So like pre-training data if you make a fun enough game. Yeah. So.
Maybe a Twitter bot to start.
Yeah.
Like a poll.
That could be a cool data set, actually. Yeah.
Have you thought about maybe using the Urban Dictionary?
Yeah, I thought about that. I also was able to find a source of like a corpus of like 1,000 or so words from like a version of this game that someone had on like GeoCities or something. It was on like the internet. It was an archived sort of web page, but yeah, so might be able to like scrape this sort of stuff as well.
So not so much a question, but just kind of like, if you want hands-on experience with these transformers, I can't recommend the Hugging Face library enough. If you're not familiar with it, go check it out. It's really good at retraining that last layer, like he was talking about, to kind of provide context on your updated corpus, even though you're still partnering with the huge library of the original corpus from the transformer.
Yeah. Here. So I second that, and I'll say at an even more basic level. So like this is all fun and games, but like I'm also doing this in a serious context where we want to like identify sort of critical information in patient records, and there's research papers that come out about like NER recognition or whatever in medical contexts, and you'll like, if you're lucky, you'll get like a GitHub repo for that paper, which came out 2 years ago. And if you're really lucky, that repo works at all. So, this is all very state of the art. So, it's hard to like take research code and get it to work. I've seen, just to give you an idea, like, you'll see references to like some file on a grad student's computer somewhere that like you're never going to be able to recreate that. But the Hugging Face library is like kind of an exceptional like example of libraries in that it's like they're both sort of like right at the forefront of research that's coming up now, and it's like good software with like tests, and so yeah.
So during masking, did it work like randomly? Because I saw in that example, it was like nitrogenous and everybody had the compound mask. How was the masking randomly weighed over different words?
Yeah, so the mask strategy again that I used was like looking at the different parts of speech, so like nouns and adverbs and adjectives, and when it found those randomly, it would mask out some of those, but not all of them. So nitrogenous was left in there just at random. You could also have a mask where like maybe nitrogenous would have been masked in a different version.
This is a question for, I guess, either of you or anyone. So I guess BERT came out, and then apparently like Sesame Street happened, and there was like so many changes and developments and advancements. The only one I know about is I think something called Roberta, where they actually took out the sentence task and it does better or something. But at a high level, like, could you speak about like what's changed since BERT came out?
Yeah, the short answer is no, I can't, because I'm also sort of a newbie in this field. But actually, so I mean that seriously. But also, like, I'm going to respond to a related question, which is like, so I'm a newbie to NLP, but not to like kind of machine learning data science stuff. I've been doing it for a while. But you would feel if you sort of read in the blogosphere about what sort of old model and new models and state of the art, you would, if you believed everything you read, you would get the sense that you're so behind on like what you actually need to be doing that there's new Roberta or Albert or whatever it is like what we should really be doing. And the whole field right now is kind of insane because it's moving way faster than any practitioner can keep up to it. I think like everyone would benefit by just taking a breath, and like BERT is fine. Like there's still plenty of, on the applied side, there's tons of ground that hasn't been explored in terms of like stuff that was coming out like 3 years ago. So yeah, that's sort of my kind of thought there, that like for practical work, just latch on to whatever is sufficiently stable and you can run with that for a while. Probably it's not optimal, but yeah, that's I think how you're gonna get the most leverage.
Also, to answer that specifically, Roberta did find that replacing the following sentence with some random one wasn't useful, but later in another BERT paper, Albert, Google refined it to just sentence ordering. So it would take two sentences, and then sometimes they would switch them, which was a more challenging task because when someone says, deriving the second parameter, I'd like to go to the store, it's obvious.
I just wanted to vote for Albert. I've used that one a little bit. The AL stands for a little BERT, so it's actually smaller from a parameter standpoint, and yet it has better performance on certain metrics. So it's just less computation, less storage size, and quite good, if not actually better. There's also GPT-2, which was put out by OpenAI, I think. That one was released, and it was like too dangerous to be released because it was going to lead to a bunch of fake news, but then it ended up being released anyway. And so they released like a small, medium, large, and pseudo-illegal version of GPT-2. But that one was, again, like what Stuart was saying, it was really just throwing more hardware at the problem. It was a different research industry that did it, and I'm sure they have their own different algorithm, but it was really just about like nothing groundbreaking, just a lot more hardware. So there's probably going to be a new one, just like Microsoft had a brand new one released last month.
Cool. Well, thanks everyone.